Hello there. In this session, we will discuss an example based on conservation of momentum, and then we will understand impulsive forces. Right. So let's take an example from our favorite sport, that is cricket. So let's say a batsman carries a bat which has a mass of 10 kg. This would be a very heavy bat, but let's just assume that its mass is 10 kg. And a cricket ball is thrown towards a batsman. Say it is given that the ball has a mass of 250 grams and moves at a speed of 40 meters per second. Now, the batsman swings his bat and he gives his bat a velocity of 20 meters per second. Right. It is also known that right after the collision, the bat comes to rest. So we have to find the speed with which this ball bounces back. Right. So once again, in this case, we are dealing with a collision. Now, as we had discussed, in case of a collision, we will always have equal and opposite forces acting. So once again, to analyze the situation, we will include both the bat and the ball in our system. So once we do that, the forces that they exert on each other are internal forces. And anyways, they are the forces which are equal and opposite, hence they give a zero resultant. Right. So as long as both of them are part of our system, we see that the net force on our system is zero. And we know that if the net force on the system is zero, that implies that momentum must remain constant. This is what we learned from the principle of conservation of momentum. Right. So in this case, we can once again write that the initial momentum should be equal to the final momentum. Now in this example, we will see that velocity, the direction of velocity will change. So in this case, we need to be very careful that momentum is a vector quantity. So this time I am drawing the arrows which we ignored the last time, because this time we would need to pay attention to the direction of motion. Right. So initial momentum is equal to the final momentum. Now since we are dealing with vectors, once again we need to decide which direction will be taken as positive. And once we decide that, the direction opposite to that will automatically become the direction which is negative. So let's just assume that this direction towards the right is the positive direction. So any vector which points in this direction will be taken as positive, and any vector that points opposite to this will be taken as negative. Right. So now we have our sign convention in place. We can write vectors with suitable signs. Let's think about momentum. So the initial momentum of the system, since once again our system is not a single body but a collection of particles, so the initial momentum will be equal to the sum of initial momentum of the two bodies which are part of the system. That is, the initial momentum is equal to the initial momentum of bat plus the initial momentum of the ball, and this should be equal to the final momentum of the bat plus the final momentum of the ball. Right. So this equation can be written by a principle of conservation of momentum. So let's now substitute values. Let's look at the first term, which is the initial momentum of the bat. Momentum, we know, is defined as mass into velocity. So let's look at the initial velocity of the bat. We know that its magnitude is 20 meters per second, and we know obviously the swing of the bat must be opposite to the direction of movement of ball. So we can say that the bat must be moving in this direction. Right. So this is the direction which we have assumed as positive, and hence the velocity, the initial velocity of the bat is positive. So the initial momentum becomes the mass of the bat into the velocity of the ball, velocity of the ball, which is plus 20, and this term clearly is 200. Right. Moving to the second term, that is initial momentum of the ball. Now the ball is moving with 40 meters per second and it is moving towards the left. Now this is the direction opposite to the one we have assumed as positive. So we would say that velocity of the ball, the initial velocity of the ball is minus 40 meters per second. Right. There's another thing to notice here, the mass given to you is in grams. Always remember, you have to substitute values after converting them into SI units. Now the SI unit for mass is kg. And I'm sure you know that to convert grams into kgs, we need to divide it by 1000. So once you divide it by 1000, you get the mass is 0.25 kgs. Right. So let's substitute these values. The mass is 0.25 into the velocity, which is minus 40. So this entire term becomes the initial momentum of the system. Right. So let's now try to write the final momentum of the system. To do that, we will first write the final momentum of the bat. Now it was given to you that right after it strikes the ball, the bat comes to rest just after the collision. So coming to rest means that the final velocity of the bat is 0. If that is the case, then its momentum is also 0. Because the velocity is 0, then mass into velocity becomes 0 automatically. Right. Now for the ball, we don't know the final velocity. We can only guess that it must be in this direction, and let's assume that its magnitude is v. Right. So now note here that no matter what direction you assume, the answer would reflect if your assumed direction was right or not. You only have to substitute value according to the direction you have assumed. For instance, I have assumed that the final velocity points towards the right, and hence when I substitute this value, I will substitute this as plus v. If finally I get my answer as a negative value, it would automatically indicate that my assumed direction was wrong. Right. So the final momentum of the ball will be written as its mass, which is 0.25 into the final velocity, which we have taken as v. Right. So let's first calculate the left hand side of this equation. The first term is 200. The second term, if you multiply this, is minus 10. So 200 minus 10 gives you 190. So 190 is equal to 0.25 times v. If you calculate this, you would see that v turns out to be 760 meter per second. Now, this is actually a very high speed, and this probably does not reflect a realistic situation, but our attention here is to understand the principle of conservation of momentum. Right. So in this case, once again, we saw that we had a system where there was a collision and there was no external interaction. So we included both the bodies as part of our system and then conserved momentum. The main thing to which you must pay attention to is that in this case, the velocities are different directions. So whenever you're dealing with momentum, remember that momentum is a vector quantity. So before writing this equation, take a direction as positive, and every vector aligned with that direction should be taken as positive, and every direction which points, every vector which points opposite to that direction should be substituted with a negative sign. Right. So now, after this, let's once again focus on the situation. So this ball was initially moving with 40 meters per second, and right after collision, it started moving with 760 meters per second. Now this is a drastic change in speed. Also, you need to think here is how long must this collision have lasted? Not for very long, right? Not even a second. It must have lasted only for a fraction of a second. So in such a small time, we saw a huge change in momentum, right? The speed went from 40 meter per second in one direction to 760 meter per second in the opposite direction. So in such situations, especially in collisions, sometimes we see that in a very small interval of time, a large force is applied which causes a sudden change in momentum. The simplest example of this is when you bounce a ball off a wall. So when you throw the ball towards a wall, let's say it goes towards the wall with a speed of v meter per second. Now you can say that after collision it comes back with nearly the same speed. So can you write the change in momentum for this? Note that initially the ball moves in one direction and finally in the other direction. So if you assume the final direction to be the one which is positive, the momentum has not remained same, but it has actually changed. The final momentum is mv minus the initial momentum, which is minus mv, because the initial vector pointed in the direction opposite to the one which is positive. So the change is minus 2 mv. So let's say if you had a 100 grams ball moving the speed of 10 meter per second, substituting values, you see that this change is equal to minus 2, right? The change in momentum. I hope you followed these steps. We basically had a ball of mass m with a speed v moving towards a wall. After collision it came back with the same speed. Then we took the direction pointing away from the wall as positive and we measured the change in momentum, which I have written as the final momentum minus the initial momentum. The initial momentum is negative for the obvious reasons we have already discussed. So the change is actually plus 2 mv, and finally we took some values to understand this case. We took the mass as 100 grams and the speed as 10 meter per second. Converting grams into kgs, I get the mass as 0.1 kg and 0.1 into 10 becomes 1. So finally I get that the change in momentum is plus 2. Right. So now the point we were discussing was that this change is brought about in a very small time, right? How long do you think a collision lasts? It could not be more than 0.1 seconds, right? It seems instantaneous, as if it takes zero time, but it still takes some time. It has to, right? So it's a fair assumption to say that this collision would have lasted for somewhat around 0.1 seconds. Now, if that was the case, then the force that acted on this ball, since we know force is change in momentum by the time taken, it becomes 2 divided by 0.1, which is 20 Newton. So, a force of 20 Newton was applied for a very small interval of time, 0.1 second, and it brought about a noticeable change in momentum. The ball completely reversed its direction. So whenever there is such a case, when in a very small interval of time a force acts and the momentum change is noticeable, in such situations the force which is applied is called the impulsive force. So impulsive force is nothing special. It is only a force. The only thing special about this is that it acts for a very small interval of time, fractions of second, and it brings about a change in momentum which is very noticeable, right? So for impulsive forces, we define a quantity which is called as impulse. An impulse, which we will denote by I, is nothing but the change in momentum. So impulse is defined as change in momentum. So you can define impulse for any force, but we talk about impulse only in cases when the force acts for a very small interval of time, right? So impulse is change in momentum. So if you think about it, look at this expression. Force is equal to change in momentum by time. So change in momentum is basically equal to force into time. So you could say that impulse is basically equal to force which acts into the time for which it acts. So impulse is basically force into time. Right. So to summarize this, we are talking about situations where a large amount of force acts for a very small interval of time. And whenever such a thing happens, the force which acts is called an impulsive force. And the change in momentum that we see is called impulse. So impulse is nothing new but only name given to the change in momentum that we see. Like in the case we had discussed, we could say that the wall applied an impulse of 2 kg meter per second. Right? Because if impulse is change in momentum, it will have the same units of momentum, which is kg meter per second. So in the case we had taken, we measured that the momentum changed by the unit 2 kg meter per second. So that implies that when the ball hit the wall applied an impulse of 2 kg meter per second. And this impulse was applied through a force of 20 newtons. Right. So this is the basic definition of impulse. In the next session, we will solve a few more examples to understand impulse in detail. Thank you.